After 10 years, the rotary engine is back and it's coming in the Mazda MX-30 Rev. Now, there's a lot that's really cool about this engine and there's some clever tricks that Mazda has employed. There's also some disappointing news that goes along with it. Now, one of the most notable changes of this engine is that you are now directly injecting fuel into the combustion chamber rather than in the intake port like was done previously. So Mazda says there's two real benefits to this. First of all, the location of where you're injecting that fuel keeps the fuel in the main area of that combustion chamber, and also you have better atomization because you're using higher pressure and a finer mist of fuel being injected, which is helpful at low temperatures such as startup. The new engine is also now using exhaust gas recirculation, which Mazda says helps with efficiency at low loads and low RPMs because it helps contain some of the heat within this engine. So Mazda engines inherently have a lot of heat loss because of so much surface area within this rotor housing. And so they say using EGR they can help reduce some of that heat loss. We're now using aluminum side housings versus iron. Mazda says this is good for 15 kilograms of weight savings. And they're also using a spray-on plasma ceramic coating that they're applying to those housing sides for better wear and better friction. They also now have wider apex seals up to 2.5 millimeters, a 25% increase, which they say gives better wear resistance. Okay, and the big kicker and the kind of disappointing news here of this new engine being introduced is that it's simply used as a range extender. So the engine spins up a generator, that generator provides power to go to a battery or to an inverter, which then powers an electric motor, which is powering the vehicle. So there's no direct link between the engine and the driven wheels. So if the rotary engine is just being used to power a generator, what's the point of using a rotary engine at all? Well, Mazda says the big advantage here is that the engine is compact. So if you compare the 0.83 liter making 74 horsepower versus BMW's inline two-cylinder used in the i3 as a range extender, that's just using 34 horsepower with a 0.65 liter. So, fairly similar in displacement, yet wildly different power numbers. And a big reason for that, of course, being that a rotary engine for each rotor has 3 active combustion chambers, which are all happening simultaneously. But there's also a big problem with rotary engines, and yet Mazda has come up with a very clever solution. So here we have our classic internal combustion engine using a piston and cylinder. And there's a technology called variable valve timing that is very common in today's engines, which are using piston cylinders. Basically what you need to know is this intake valve, which opens and closes in order for you to pull in that fresh air to use with combustion. If you close it too early, well, you don't let enough air within the cylinder, right? And then if you leave it open for a really long time, well, then you let some of that airflow go back into the intake, and eventually that piston starts moving up and pushing more of that air out, effectively reducing your compression ratio. With internal combustion engines using piston cylinder devices, we have variable valve timing and we can change it throughout that RPM range. So, can you do that with a rotary? Well, not exactly, right? Because we have this simple port, and that port, whenever it's exposed to the intake chamber here within our combustion chamber, that's when you can pull air in. And then once that rotor covers up that valve, well, then you can't pull in any more air, right? You don't really have control over when this is open. So you do have control over how you design this overall engine, and you can optimize it for one specific RPM, but you can't optimize it throughout the whole range, unlike what you can do with piston cylinder engines. Now, one of the options Mazda describes in this patent is that they add an additional electric motor that's going to be directly linked to the eccentric shaft of your rotary engine in order to manipulate the speed of your rotor's rotation. So why would you want to do this? Well, again, remember, for low RPM, we want less time for our intake to be open. For high RPM, we want more time for our intake open so we can get more air into the engine. So, here's a little chart that shows the logic of how this electric motor is going to work. Basically, the way we're going to set up the engine is so that at the RPM that we use the most, and keep in mind, as a generator, there's going to be like one set, nice, efficient RPM where this thing's cranking out a good amount of power. So we're going to pick that RPM where we're efficiently generating power that we think the engine will sit at the most frequently, and that's going to be our zero assist spot, meaning this motor is doing absolutely nothing to aid the rotation of this rotor. But if we're at a lower RPM, then we're going to help speed up that rotation. And if we're at a higher RPM, we're going to slow down that rotation for a portion of it. So if we look at our intake stroke here for the rotary engine, this little Dorito here is going to rotate, and that's going to cause our eccentric shaft to rotate 270 degrees. Well, throughout that rotation, that's the total amount of degrees of rotation that we have for our intake stroke. So for the initial bit, we're not going to do anything. We're not influencing in any way. But right at the end, we're going to use our electric motor to change the speed of that rotation. And that speed change is dependent on where our RPM is. So again, if our RPM is really low, then we're going to add a positive assist of torque. That motor is going to help speed up the rotation so that you have less time for intake. And then if you're at a really high RPM, meaning this speed right here is really fast, well then you slow down that rotor very briefly at the end of its intake stroke in order to give it more time for air to come in. And then you turn that assist off again, and it maintains its rotation at a higher RPM, but it slows it down just for that little bit at the end so you can get more air within the engine. Okay, option 2 as described by the patent, and this is extremely clever because instead of using this additional motor and inverter, we're going to simply use the generator to do that job. Now, one of the key differences here, previously we designed an engine such that the most frequently used RPM gave us our maximum intake charge air efficiency. So the overall design of the engine is designed for one specific RPM, and at that specific RPM we have our maximum intake charge efficiency, and thus we don't need to use any assist from the motor. Now our most efficient RPM for intake charge efficiency is the highest RPM we're going to use. Again, we want the longest duration for our highest RPM. So that is the location where we provide no assist. And so how do you provide a torque boost with a generator that you're using to generate electricity? Well, basically what you're doing is you're using this generator like a brake. When it's generating electricity, this generator acts like a brake. It's providing a torque that this engine has to overcome. For a brief moment, you can basically shut that off. You can reduce the torque requested. There's an electricity generation torque, and you're reducing that request by a certain amount. So that is what you're doing as you're using lower RPM, and if you were to be at the maximum RPM, then you're simply not requiring that generator to change its load at all.